stronger than dispersion forces. However, there's one situation where this does not hold up. How often does AP test it? Enough for me to explain it. Alright, so here, let's take a look at two structures where we might have thought the answer was one way, but the answer is the opposite way. So we have something unexpected. I'm going to draw out CH3Cl. And then for comparison, take a look at switching it to CI4. So 4 iodines on the outside. Okay, so in taking a look at these two structures, the first thing is, if we're making a comparison, right, the one on the left, would you consider that structure to be polar or non-polar?
Polar.
Polar, right? Because we see an uneven distribution of electrons, especially toward the chlorine side. But if we're looking at CI4, would we consider this molecule to be polar or non-polar?
Non-polar.
Non-polar, right? We have an even distribution among all the outside atoms, especially since they're all the same elements. Okay? So the concern would be, out of these two, this one can offer dipole-dipole. This one can offer just dispersion only. So the second one is dispersion only. Whereas the first one, if we had a dipole interaction, we know that the chlorine side of the molecule is delta which way? Plus or minus?
Minus.
Minus. And then the hydrogen side is delta positive. Okay, so how does AP test this exception? Well, here's what AP is going to do. AP is going to list boiling point temperatures, or they could ask melting point temperatures. The concept is still the same. Alright, so they present to us that the boiling point for this molecule is negative 24.2 degrees Celsius. Now, generally speaking, the higher ranking the intermolecular force is, the higher the boiling point should be. So in the case of these two, where this one offers a dipole-dipole interaction, which is higher in rank than this one, which offers dispersion only, if we had the boiling point value of the molecule on the right, would we have expected the temperature to be higher or lower than the negative 24.2?
Lower.
We would have expected it to be lower because this one's lower ranking. Okay? Now, on the AP exam, they provide us the boiling point temperature for this molecule, and unfortunately, here's the temperature, 329.2 degrees Celsius. So this goes against the pattern for the ranking system. Okay, so without going into all of the details, because we don't need to, mercifully, the reason for this to go against the pattern of our ranking system is actually something we've covered. Polarizability again. Now we said, generally speaking, we would use polarizability as a tiebreaker procedure if we had looked at two species that had dispersion only. However, polarizability has a chance to outrank dipole-dipole. Okay, how often? Well, enough for us to care. So we have an outranking possibility with polarizability, especially if the number of electrons differs greatly. Unfortunately, there's no set number to tell you about when the outranking takes place. It's a total gray area, all right? So if you're wondering how does AP frame the question, here's what happens. AP usually sets up the question like this, where they give you both molecule structures, and they give you both molecules temperatures. what they ask you to do is to explain why the temperatures look that way. Okay? So if they present it to you like this, with the given temperatures, you cannot use the ranking systems to classify the temperatures at all, right? Because you would have expected that since this one offers dipole-dipole interactions, which is a stronger intermolecular force, that the boiling point would be higher. However, that's not true here. So when you see that happen, where it doesn't match up to your ranking system, okay, you're allowed to explain it in terms of polarizability. So again, same concept, right? We're going to say that Ci4 is more polarizable than this CH3Cl because Ci4 has how many valence electrons?
12. Wait, which one?
32?
35.
Oh,
Thirty-
so,
How are you getting 35?
Wait.
Odd number don't work here.
22. 32.
7 times 4.
32.
That's 32. Okay.
I was thinking lone pairs.
Moving over. How many valence electrons does this one offer?
14.
14. Okay, so since Ci4 is more polarizable with 32 electrons to distort compared to just 14 for CH3Cl, right? Polarizability is the reason for the boiling point temperature of Ci4 being so much higher. Okay? So again, on the AP exam, they'll use temperature values for the comparison. Alright? I have not, to alleviate this intimidation, I have not seen on the AP exam where they do this and ask you which one's going to have the higher boiling point. Alright? So they haven't done that. They've done it this way. They go, hey, the temperatures are here. Does it make sense to the ranking system? Well, not this one. Alright? And if it doesn't make sense, again, this is where you go. Alright? So just keep that in mind that this is a tie-break system as well as a possible outranking system if the temperature values do not make sense. Okay? So just a heads up on it. Alright. The other issue. The other issue focuses on taking a look at structures like these. And I feel like I'm teaching organic, but not really. Oh, so 4 carbons going across, and then just put H's. And then for comparison, what I'm going to do now is draw 3 carbons going across. And then the 4th carbon goes here instead, so it's going to be like a branch. Same thing. Remaining slots or remaining bonds are to hydrogen. Now again, on the AP exam, you don't draw this from scratch. This is provided. Alright, so as you're wrapping this up, I have one frame of framing question for the problem, which is, take a look at the 2 structures. Are both of them the same chemical formula?
Yes.
They are, okay? So if they're both the same chemical formula, before I even show you anything with temperatures, can I use polarizability?
No.
No, same. If it's same chemical formula, it's the same number of electrons. So it can't use polarizability. Alright? So, since I cannot use polarizability, here's the next thing. Polar or non-polar?
Cold. Not cold.
Non-polar, right? Look at all of our central atoms, look at all the outside. Polar or non-polar?
Non-polar.
So both of them are non-polar. Both of them are the same chemical formula. Alright, so we can't do dipole-dipole. That means in terms of these two for intermolecular forces, right now it looks like they're the same. So, again, on the AP exam, they're going to give you temperatures to look at. And they tell you the one on the left, boiling point temperature, kind of a weird number, negative 0.5. And then the one on the right which has the same chemical formula and is also nonpolar, we would expect the boiling point then to be, what do you think?
The same.
The same, right? Because we have the same intermolecular forces, same chemical formula, and we can't use the trick question because it's the same number of electrons. So, we expect the same temperature. It's not. So, based on what we're seeing here, without knowing what's happening, which one ends up having a stronger intermolecular force somehow?
No, the first one.
The first one. Okay. As for why this one for some reason has a higher boiling point, again, I'm trying not to intrude too much into your math teacher's domain. I'm sorry. Okay.
Just do it right.
So here's what's happening. All I'm going to teach here as to what you can say on the AP exam, okay, the technical term is surface area to volume ratio. I'm not going to teach it out there. Instead, I'm going to teach it like this. This molecule, okay, has what's called a straight chain of carbons. And if we were to build it, okay, this molecule is pretty flat going across. All right, even though the angles don't make sense. This molecule, on the other hand, if I tried to build it in 3D, is not going to be flat going across because I have a branch sitting here. All right, so what ends up happening is that for some reason, these flatter, quote unquote, molecules actually can distort electrons a lot easier than the rounder molecules. Now, if you have trouble seeing flat versus round, which means you're struggling with what the Earth is supposed to look like. Worksheet 2 has a good example of this, so I'm going to show you worksheet 2. On the AP exam, they will give you these drawings, okay? And actually, these drawings are for the formulas that we're working on, C4H10, right? This one's the quote-unquote flatter version. This one's the quote-unquote branched one, which makes it rounder, okay? So what ends up happening is, it's easier for a flatter structure to distort the electrons and make it lopsided, especially as you're going left to right or up and down, whereas here, it's harder to distort, okay? Because you have a round shape. It's harder to get the electrons to be lopsided in a certain way, okay? So again, in terms of explaining which two has what, all right, because this has an easier time distorting the electrons to create those induced dipoles, we expect this form to have a higher intermolecular force, leading to a higher boiling point, okay? So here, this leads to creating more induced dipoles, which increases the boiling point. All right, so kind of a weird situations in terms of exceptions here, where we have something that goes against the pattern, and then we have something where you have to pay attention to how it's drawn. Okay, so generally speaking, the longer your straight chain, right, 4 carbons versus 3, the longer your straight chain, the higher the boiling point should be. Okay. All right. So I mentioned about NH3, so let me address that. So I want to call this